Let's talk some history of combustion in a minute and a half. Mankind has been closely associated with fire. The mastery of fire began over a million years ago with Homo erectus, and Neanderthals later used it to improve living conditions. Early uses included hardening tools and creating light. With the advent of farming and sedentary life, fire was used in pottery and metalwork. The mastery of bronze, iron, and steel marked significant progress in civilization, with blacksmiths controlling the quality of tools and weapons. The arrival of gunpowder in the 15th century, originating from China and spreading to Europe, revolutionized combat tactics. Gunpowder's composition was known in Europe by the 13th century, but effective firearm use began in the late 14th century, impacting historical events like the Hundred Years' War and the rise of Muscovite Tsars. The invention of cannons during the wars of religion in France made traditional defenses obsolete. The Industrial Revolution, fueled by coal, led to advancements in thermal machines, heavy industry, and transportation. With the advent of advancements in metallurgy, we could now focus on forging metals of better quality, better strength, meaning they could sustain more loads, giving rise to all sorts of development marvels, including high-rise buildings and bridges. Of course, this came at a cost of air pollution. The development of internal combustion engine for transportation made the world a smaller place, and later, with the invention of turbo engines for the skies, made it an even smaller one.
5, 3, 2, 1, 0, and lift off.
Rocket engines and artificial satellites ushered in a new era of communication. We are no longer bound to Earth. Our journey can be beyond what we see around us. What started as a curious pursuit ended up with a marvel, all possible through precise understanding of combustion. Hello all, welcome to the video series on combustion. Today we'll start with something boring. This is a boring video about chemistry in OpenFOAM part 1. In part 1, we'll learn about the multi-component fluid problem. If you wish to follow, please ensure you have OpenFOAM version 12 from openfoam.org installed. Also, if you are a Windows user, please make sure you're running OpenFOAM from WSL2. I will add the link in description on how you can install both. Also, it goes without saying that you need to have some basic level knowledge of fluid dynamics, thermodynamics, chemistry, chemical reactions, and CFD with some OpenFOAM background. So, let's begin with the multi-component fluids. When we usually perform analysis, we consider fluids to be a single component or just one fluid that doesn't undergo chemical changes even though heat transfer may occur. Take air for instance. Air is quite a stable mixture of different components and doesn't change much unless high amounts of heat are supplied to it. It comprises of a bunch of molecules which vary in their composition and also vary based on location around the earth, water vapor not mentioned here. You can see that the majority of air consists of nitrogen, oxygen, argon and others, and if we look closer at the other sections, we can see trace amounts of carbon dioxide, neon, helium, methane, krypton and hydrogen. Speaking of methane, think about how when natural gas is taken out of the pockets in mines, it is burnt on tall structures. The reaction might look something like this. Of course, this is an idealized form of the reaction, but bear with me for a bit. 1 part methane combined with 2 parts oxygen in the air with little energy given to it can give out 1 part carbon dioxide and 2 parts water and releases a lot of energy with it. We can see here that the combustion process is tied to energy. There is a give and take here. We are giving some energy initially in anticipation of getting more. In essence, there are very fast chemical reactions occurring while fuel and its oxidizer are present. All chemical compounds have bonds between atoms or molecules. These bonds possess potential energy. If the bonds are broken, this tends to produce some useful energy. Once the bonds are broken, the atoms or molecules would want to form other bonds while losing energy in the form of heat. Chemical reactions include certain types of energies. One such energy is called the internal energy. Think about the inherent movement of molecules in space and time. Molecules have free rein in how they want to move. They could translate, possessing kinetic energy. They could rotate or vibrate. Molecules can rotate around multiple axes, but having them moving makes them possess some amount of kinetic energy. Now, let's take this water molecule with the white blobs representing hydrogen, pink blob in the middle representing oxygen. The 2 hydrogen and 1 oxygen form what is called a polar covalent bond. Hydrogen atoms each contain 1 electron and 1 proton, with the electron ring of hydrogen preferring to possess 2 electrons to create a stable configuration. Oxygen has 8 electrons, but it wants 2 more. It has 2 rings of electrons, with the inner ring having 2 electrons and the outer ring having 6. But it's not happy with this arrangement because 8 electrons is the stable configuration for oxygen. Both oxygen and hydrogen want to be happy and have a stable configuration, but they can't do it on their own. So they come up with a plan. They'll share electrons. This is like an energy treaty between them. Oxygen shares one of its outer electrons with each of the 2 hydrogen atoms, and each of the hydrogen atoms shares its one and only electron with oxygen. This is called a covalent bond. Now, each hydrogen atom thinks it has 2 electrons, and the oxygen atom thinks it has 8 outer electrons, and everyone's happy. This is the internal energy we are talking about. Energy possessed within the molecule by virtue of its motion and the bonds it possesses. Now, chemical reactions also include something called enthalpy. Imagine a bunch of these molecules existing willy-nilly in space and doing their own thing. Assuming these molecules encounter a wall together, they would form some amount of force on this wall. So the concept of enthalpy talks about the capacity of a group of molecules to do work. Notice we say group, not a single molecule. It takes a considerable amount of force to exert something like pressure or temperature, which is not possible with just one molecule. Enthalpy is a measure of that phenomenon. So our chemical reaction now makes a little more sense. We have internal energy by virtue of the motion of molecules and bonds forming / breaking. Also we have enthalpy because molecules are moving in a group to exert some work. So we learn now that chemical reactions require energy. The net energy is simply a subtraction of energy required for forming the bonds and energy required for breaking the bonds. Now, if this subtraction results in a positive net, this would mean we gained energy, whereas if this results in a negative net, this would mean we lost energy. So to summarize, multi-component fluids have multiple components of fluids, so to speak, which can undergo chemical changes. We need to keep track of the chemical changes as well as positional changes to fully explain what is happening to the flow. We also want to ensure energy is balanced, that is, it is accounted for at all times. In the next part, we'll learn about the thermophysical models. Stay tuned.